introduction. It's wonderful to see all of you in this seminar and in this mathematically interesting day. You know, in the day today, we have everywhere the number 2. It's the 22nd day of the month and the second month of the year 22. And it's also Tuesday, so it's indeed a big numerological event. Okay, so this talk is based on our joint work with Toru Ozawa from Waseda University. Detailed proofs and reference can be found in our archive paper. This presentation has simple structure. We start with a brief introduction and motivation. Then we will present main results. After that, we will continue our discussions with particular cases and some applications. So here we have a classical Poincare inequality. So it's given by formula 1. And this inequality is closely related to the Dirichlet-Laplace. And here, indeed, we have sharp inequality, and the constant here, lambda, is the first eigenvalue of the Dirichlet-Laplace. It's a well-known inequality, and it's sometimes, in some literature, it's called Steklov inequality, especially in one-dimensional cases. And also some higher order cases can be called Friedrich inequality, but this is our main topic today. We will discuss about it. So this is classical case, and it's very important tool in PDE, and there are many extensions, generalizations, and different versions of this inequality for some the corresponding needs in the theory of PDEs. One of possible extensions is a so-called LP version of this inequality. So LP version of this inequality is given by formula 2. And it's known that there exists some constant which depends on omega, and P omega is just, the set. In general, it's a hard task to find the characterization of the constant C in general, because it only depends on omega and P, but it depends indeed the geometry of omega. So if, for example, if we change a little bit shape of omega, then the C, the constant, depends on that omega. So that makes difficult to characterize, to make characterization of this constant in general. But as we see in L2 case, it can be characterized by lambda 1, the eigenvalue of the Laplacian, but in general, in LP case, it's indeed hard task. For simplicity, we just call all these type of inequalities by the Poincare inequality. Okay, so there are many proofs of the Poincare inequality, but we do not go into the details. To the best of our knowledge in literature, there are 3 main problems are considered studied separately. The first question is, of course, when we talk about Poincare of inequality, it's about proof of the inequality with some constant. For many studies, the rough inequality is already sufficient to continue their studies, to apply this inequality as tool, for example, for some existence results and so on. Another important question is that characterization of best constant and its existence. So that's the question we started about the LP Poincare inequality. And third important question is characterization of non-trivial extremizers and their existence. So it's now we are talking about some the elements, some functions for which the best constant can be reached, or at least it can be extremized. However, if one obtains a remainder formula for the Poincare inequality, then it follows the proof of the Poincare inequality and the characterization of the best constant, as well as characterization of non-trivial extremizers. So remainder term analysis gives an answer to these three questions at once. So that's the main motivation why studying remainder term formulas for these type of inequalities are important. So that this is the main motivation. Let's consider vector fields over some open set omega in Rn. So we denote by here, we denote by x with lower index k a vector field in Rn, and their corresponding gradient can be denoted by just a capital X without index. Okay, so we use this notation L to express the corresponding sum of squares operator. So the formula 4 gives the corresponding sum of squares operator. In general, our analysis, indeed, the paper which we wrote together with Professor Ozawa, that paper is about vector fields over manifolds, Riemann manifolds, sub-Riemann manifolds. But for simplicity, in this talk, we'll focus only on vector fields in Rn. So let's quickly recall the definition of vector fields in Rn. So we understand by a vector field the first order linear differential operator. So this is the formula for our vector field. Okay, so here we have some coefficient function, and which is a scalar function. And so we fix k for a given vector field, and then we have here n tuple of scalar functions. And so we started our discussion here, some smooth real vector field. So what smooth means? Smooth means that our scalar functions are smooth functions, and real means we are only interested in real value functions. But in general, some of our arguments also can be considered for the functions, complex valued functions. But let's make this presentation simpler, and so I believe we will reach our aim quickly. Okay, so what's the action of this vector field to a function? So it's trivial. So the action means that, and this is another function which is given by this formula, assuming that the f is some differential function. Okay, so that's these are about our notations. Okay, so here we have our main theorem. And it assumes that our sum of squares operator has some positive eigenfunction and eigenvalue. Okay, so if we can find some function which satisfies this equality, okay, in omega, and find there exists a number lambda, then for smooth functions, we have this algebraic relation. So it says that if we consider a difference of these two terms on the left-hand side, okay. So here we have simple terms. So since here we have gradients, the first model can be considered as a length of this vector. And if you take a square of that, then subtract. Since we agreed that u is real valued, so we can focus in this presentation real valued functions. So here, this model just can be removed, but still with this notation we have on the left hand side, lambda is a scalar, which is taken from the assumption. So this difference can be computed represented in terms of some sums which are written in terms of the sum of squares operator. So on the right hand side, everywhere we have the operator L. So this is the first relation. Here we assume, we say that the U is smooth function. Indeed, this regularity of U can be expressed in terms of M. But for simplicity, I put here infinity, but indeed one can remove infinity. So it can be seen on the right-hand side, the regularity on the regularity of the function U. So this is nothing but just a pure algebraic relation, and it can be proved by using properties of vector fields and a combination of mathematical induction idea with rescaling properties of sum of squares operator. So straightforward computations can be done to obtain this equality, but of course not trivial computations should be done to obtain this relation. So as you see here, we have even degrees, so 2m, and there we have also 2n on the left hand side. What if we consider odd degrees? In that case, again, we have the same statement, and with the same assumptions. For smooth functions U, we have this another algebraic relation, which is different from the previous even case. On the right hand side, there are also some additional terms appear for the case when we have an odd degree on the left hand side. The rest, the idea is the same, and the proof is slightly different, but the main idea is again remains the same. That's application of properties of vector fields and a combination of induction type iteration process with rescaling properties of the sum of squares operator. So these are main relations, and why these relations can be useful. Let's return back to the definition of vector fields here. Okay, so we want to see some classical, some usual operators here. Let's consider just the classical case. So let's consider instead of xk, derivative with respect to the component, the component of this Euclidean space with respect to the direction k, xk, okay, small xk. So let's have here just not sum, but instead of xk, let's have the partial derivative k, okay? So in that case, we get instead of this gradient, we have the usual standard Euclidean gradient. So everywhere we have just the derivatives. Okay. Of course, we should assume in that case the capital N is equal to the small n, and the corresponding the sum of squares operator will be the Laplacian. Okay. So let's focus in that particular case, and we can of course flag in instead of this L Laplacian, instead of the capital X the usual gradient. And in that case, we will have the classical case, and now we can take integral over omega. Okay, so if we take integral over omega, for example here, and using some direct computation on the right hand side, for example, we can use the divergence formula, and for that we may need some assumptions on omega, but still that can be done directly. So that gives us this beautiful formula. So it says that the difference, so here we have a higher order term Poincare in Poincare inequality, and if we take difference of the between these terms, then this difference can be expressed explicitly in terms of sum of some positive values. So please pay attention on the right-hand side of this equality. Then you see here everywhere positive numbers. So we also here we had an assumption that the operator L must have some strictly positive eigenfunction in omega, on omega. Okay, it's the case for the classical Dirichlet Laplacian. Well, it needs the classical Dirichlet Laplacian satisfies this assumption, because in that it's known from the spectral theory that the first eigenvalue is always positive, and the corresponding first eigenfunction is always positive, and the corresponding, since it's positive operator, the corresponding eigenvalue is also positive. Indeed, in classical case, we have very nice operator, which is compact self-adjoint, and everything is fine there. So we just instead of that lambda, we can take the first eigenvalue of the Dirichlet Laplacian, and instead of the psi there, we can take U1. So U1 here, U1 here is just the first or the ground state of the Dirichlet Laplacian in omega. Okay, so that algebraic relation gives us this so-called the remainder term formula for the higher order Poincare inequality. And obviously, just since we have on the right-hand side positive term, that means everything is greater than 0, and it directly follows the higher order Poincare inequality in the case when we have the order here is even. And how about the odd case? And it's the same. Yeah, it's the same. So the Bruce discussions, they can be just directly extended to this case, but the only difference here is that on the right-hand side we have some extra term, but still this extra term is positive. So, and the conclusion can be the draw. So those algebraic relations imply in the classical case, for example, the remainder term formula for the higher order Poincare inequality. Okay, but if we pay attention closely, then we see here, yeah, it's fine that we have higher order case, but everywhere we have L2 norm. So it indeed gives us the remainder formula for L2 Poincare inequality. But how about LP case? So that's the second question. So if we apply our techniques, which we use to obtain these algebraic relations, then that technique gives us this relation. So this is the first step, first attempt to get some remainder formula for LP case. Okay, so I just need to check if okay, or sometimes yeah, I can check, because sometimes it's, you know, if something wrong with the internet, I can be speaking. Okay, so so this is some attempt for to try to get LP case. Okay, so again, if we apply that technique, the rescaling properties, then this algebraic relation can be obtained. And the interesting thing is here is that this is some number. Okay, so here we previously we didn't observe this number on the left-hand side. This is indeed about our lambda. Yeah, if we it is our lambda. So in L2 case we had this term, so that that gave us the remainder formula. But in LP case, in addition to this lambda, we have another number. This is interesting number, and it has explicit formula. And another thing is that, and another weakness of this formula is that we are able to obtain this only in the case this p, the degree is some power of some degree of 2. Okay, only in this case, at least, as far as we know, only in this case, our technique works to obtain the relation. Okay, so how about this number? So if we analyze this number, then first of all, we have this nice estimate for this number from the right and from the left. And thanks to this two-sided estimates, we can obtain the asymptotics of this number. So today we have everywhere 2. So the answer is here is 2. And if we repeat the same process which was done for the L2 case, that's if we take integral over omega from here, yeah, and substitute the classical operators. So instead of x here, we can take the classical gradient, and instead of L here, we can take the corresponding sum of squares of operator, which is the Laplacian. And in that case, our previous relation gives us this formula. And on the left-hand side, we have some difference. It looks like some remainder formula, but the problem is that here, because if this value is negative, okay, in that case, it gives nothing, because if so great, on the right-hand side, we have positive term, and that gives us some information that this difference is indeed positive. But how about the relation between the lambda 1 and this number sigma m is important to obtain the remainder formula. In other words, if this difference is here, this difference is negative, then our technique indeed fails. So it gives nothing. It's not indeed what we wanted. But in the case if this number is less than lambda 1, then it gives something. At least, again, sharpness is not clear, because in this case, on the right-hand side, to do the next step, to analyze, to find extremizers, to analyze characterization of this a constant, if it is optimal or not, we need to study this the term on the right-hand side. So we need to analyze when these terms 0 vanishes or not. But that's difficult task, and it indeed I believe that it doesn't give a sharpness there. But still, I repeat again, if this number is less than the first eigenvalue in classical case, we are just now talking about the classical case, okay? We are talking about the Dirichlet Laplace. So in that case, we can get some LP version, but P is a very special number here, just to this degree of the 2, but still, our technique gives some information, but it is not, of course, it's not enough to answer to the question, to the open question that's about finding, it's here, that's about finding the exact remainder term for the LP Poincare inequality. So this problem is still open, but what we have, the formula 10, is just some attempt to obtain that remainder formula for LP Poincare inequality. Okay, so how about the applications of what those remainder formulas, higher order remainder formulas, they give? Okay, so one of possible applications is in Lie groups in Rn. So here we have a definition of so-called stratified Lie groups, which was invented by Gerald Folland. And it says that a Lie group in Rn with some operation is said to be stratified group if these two conditions are satisfied. So first condition is about the existence of automorphism, so which indeed that should be dilation given by this formula. And the second
yes.
Second condition is that the vector fields from the first strata must satisfy so-called the Hörman's rank condition. Okay, so if these two conditions are satisfied for a Lie group in Rn, then it's called stratified Lie groups. It's very important class of Lie groups, which is connected to so-called lifting theorem, and it plays important role in the theory of subelliptic equations and in the theory of subriemann geometry. But what we want is that to get some interpretation of our theorem, the main theorem. So what that main theorem may give, for example, in this theory. Okay. So here we have the sum of squares operator. It's called sub-Laplacian, and this is subelliptic differential operator, and also the corresponding gradient, so-called horizontal gradient. It's not full gradient, but still it's some gradient, so it's called horizontal gradient, and it can be denoted by nabla h. And so these are the main operators we need. Well, these are operators which are involved in our algebraic relation. Okay, so let's go back to our, so instead of now this x, here we have some so-called horizontal gradient. Instead of L, now we have a sub-Laplacian. Okay. So we can just flag in those, because this theorem is about general vector fields. So we can, of course, use this relation for stratified groups. Okay. Here we have some examples. The first example is trivial example, which is the only commutative group in this class, which is abelian group, usual Euclidean group, and it's trivial is stratified, and we just need to take the topological dimension.
Oh,
the group must be equal to the dimension of the first strata. In that case, so we have only one strata, which is the whole Rn. So in that case, it gives us a stratified group. But it's as I said, it's the only abelian case. And the other groups in this class, they are non-commutative. One of the most popular group is the so-called Heisenberg group, and it has these vector fields. Okay, so for the first strata, we have it only has two strata. So for first strata, we have these vector fields, and we can again, instead of these vector fields, we can use these first strata vector fields. So we can construct the horizontal gradient and the corresponding sub-Laplacian. So we can apply in the Heisenberg group, we can apply our previous theorem. So what's the conclusion in this conclusion of that theorem in this field? Okay, so let's consider not higher order case, but just let's take the m equals to 1. Okay, the first order case. In that case, first order case, our theorem follows this equality. Okay, so well, one can just need to substitute everything in the general theorem. So we obtain this relation on the stratified groups. And here we have on the right-hand side some on the left-hand side, we have a positive term that's good. On the right-hand side, we have some relation. So we have gradient, and also this we have this coefficient, okay, in terms of the phi. Okay. Now we had that assumption that to have here, now we want to have some scalar here instead of this expression. So to get that lambda, we need to have that assumptions which satisfy. So if we assume that there is positive eigenvalue for the sublaplacian and the corresponding eigenfunction, then in stratified groups we can obtain sharp Poincare inequality. In our previous papers.
Excuse me.
Yes,
me. Durvudkhan.
Yes.
Yes.
I can't hear you. Hello.
You're welcome, Durvudkhan.
Yes, there was a question, but
continuation after.
What?
After.
Okay.
Not question.
Okay. Later. Okay. So yes, maybe that question is about the existence of these eigenvalues and positive eigenvalues and eigenfunctions. But that's an important question. And in general, of course, there's no the positive answer to this. But at least for in this case, it's trivial case we already know. But on Heisenberg groups, it's also known that the so-called nodal domains, so positivity of first eigenvalue is known in Heisenberg group. It's already known. So good news here is that it's not empty conclusion. And at least it gives sharp Poincare inequality on the Heisenberg group. So and also there are also H-type groups on which one can extend these conclusions without assumptions. And why this is important, because in our previous studies with Professor Michael Rojansky, we did some progress and we obtained a Poincare inequality on the Heisenberg groups, but without sharp constant. So for us, the question was open. So at least these relations give us some hint. So it hints us that if everything fine with this spectral theory, in other words, the first eigenvalue and first eigenfunction is positive, then the sharp Poincare inequality is guaranteed. So that it's the final conclusion, and it gives us this theorem. Okay, that was about stratified groups. So what if we go out of the class of stratified groups? So let's consider so-called famous vector fields, so-called Wernicke-Grushin type vector fields. So indeed here we have Wernicke-Grushin vector fields. But these vector fields, they will not give us the algebra. So it doesn't belong to the class of stratified groups. Even in general, these vector fields do not satisfy the the Hermann rank conditions in general. Only in the case if this gamma is even integer, in that case which satisfies this rank condition. Otherwise, the Grushin vector fields they do not satisfy even the Hermann's condition. Okay, so here we have some special vector fields. It has a long history and many applications, but we are interested only in some applications, some consequences of our theorem. So we apply our theorem because we did some search with Nur-Sultan that if there is sharp Poincare inequality for these vector fields. So we found out that there's no such result in literature. So so of course, applying our theorem to these type of vector fields was important. Okay, so first thing is that what's gradient here? Gradient is simply just it can be denoted by nabla gamma, and it's just a collection of these vector fields. And what's the sum of squares operator, which is again, it can be written directly, and it has, of course, direct relation with the standard Laplacians. Okay, so we have the two operators, gradient and sum of squares operators. So we can, again, as we did in the case of stratified groups, we just can flag in everything into the relation. So that gives us this relation. Okay, the formula 15, and on the left hand side again we have positive term. That's good news. So it gives us at least some inequality, a Poincare type inequality. And now the second question is important questions about to understand these coefficients we have. So here we have to understand this coefficient. So we want to express it in terms of some scalar. Okay, so as we did before, so we need to have some assumption, existence of a positive eigenfunction and positive eigenvalue. It is indeed not well, it's in general, it's not elliptic operator. It's not, the spectral theory is not trivial here. But still, with the previous assumption, we can obtain very nice relation, which gives not only the Poincare inequality, but it also gives the Sharp constant, and it also gives the extremizer of characterization of extremizer for this constant. So all the information is here we wanted. So in the beginning we started. Remember we were interested in three main questions about the proof of inequality, characterization of the constant, the Sharp constant, and characterization of extremizer. So this simple equality gives all this information. So we have the answers to at once. So to these three questions here, all the important thing is about this assumption. Yeah. So and here we have good news for this operator. It's known that the spectrum is positive, and also the positivity of the corresponding eigenfunction is also studied well. So it's studied in this work. So now we know that so those omega domains in which this assumption is guaranteed. So that thanks to that the previous work in spectral theory now, and combining that with our remainder term formula, now we have the full answer to the question related to the Poincare inequality. So now we have a Poincare inequality for the Grushin operator, and we also know that it's Sharp, and we have the characterization of the extremizer. Okay, so now about applications, of course, as in classical case, Poincare inequality has many applications. One of them is, for example, if you consider this nonlinear problem for heat equation for the Grushin operator, then let's take on the right-hand side some nonlinearity. So here we have famous nonlinearity, so-called Fisher-Kolmogorov, Fisher-KPP nonlinearity. In that case, thanks to that Sharp Poincare inequality, we can identify the exact blow-up time. So we have here lambda 1, which is the first eigenvalue here in this guy. Okay, and U1, which is the corresponding. Of course, for omega, we use assumption from this paper. Okay, so everything must work for ideally here. So under this assumption, okay, so here we have initial condition, initial data, and under this assumption, we can identify exact blow-off time for this nonlinear problem for the heat when the Grothendieck type operator. So the answer here is that the solution of this problem blows up in this time. Okay, so let's consider the more general case. So here we have some general case, and that attempt is just to extend this the nonlinearity on the right hand side. So we need that Lipschitz condition for F with some additional properties. One can, again, by applying that sharp Poincare inequality, one can obtain the blow-up results for this general case, but under certain assumptions. And this also gives us that in this case we also have some blow-up time, and the estimate for the blow-up time also can be given by some explicit expression. So these are all. Thank you for your attention.
Thank you,